Hello everyone. Today we're going to demo the NEC cable sizing calculator. You can find this calculator at elect.com/calculators. First, we're going to look at the load tab. In the load tab, we're going to define the load current and the power factor at which that load current is being drawn. We also have an option for continuous here in NEC. As per NEC's definition, when you check continuous on, the load is expected to run more than 3 hours. And as per NEC, if the load runs more than 3 hours, that load has to be rated to 125% of the rating. So when I check this on, instead of 100 amps, I have to size my cables at 125 amps because the load is continuous. This is for safety purposes. We can also add harmonics to this particular load profile. So let's say on top of my 100 amps, I add even harmonics of 5 amps and triplet harmonics of, let's say, 25 amps. And then I can click on the update button to basically add these harmonics into the load current. And in the detail section, I should be able to see the true RMS currents that are basically resulting from the fundamental current and the harmonics current. We have defined the load current. We basically go to the supply tab. Now NEC doesn't make it mandatory for people to always consider voltage drop calculations. So if a user wants to exclude voltage drop, we have a checkbox here. When you click on this exclude voltage drop calculations, you basically bypass the voltage drop calculations and your cable sizing results are solely based on the load current and the ampacity calculations. But let's say if you want to include the voltage drop calculations, you basically input the voltage drop percentage. As per NEC, 3% is the allowed branch circuit limit and 5% for the feeder. You also define the length of run from supply to load in feet. That basically directly impacts your voltage drop calculations. You also define your supply fault current. This is used for the available fault current at the end of the run calculations. So you basically define what is the fault current at the source end that you expect, and based on this we calculate like the available fault current at the load end as well. Moreover, we can also change our voltage levels up to 1000 volt over here. So after finalizing our supply parameters, we go into the cable tab. In the cable tab, we're going to select a particular insulation. There's the drop down list of insulations available. All these insulations are as per NEC article 310.4. There's a table of insulations that are suitable or usable in NEC. Those insulations are available here. So we select a particular insulation that we're going to use for this cable sizing scenario. We also select the phase conductor material. We have options for copper, aluminum, copper clad aluminum, nickel, nickel coated copper, which are mostly used for higher temperature applications. We have conductor materials for your equipment grounding conductor, and we can also select the core, whether it's a single core cable or it's a multi-core cable, multi-conductor or single conductor cable. So, based on our supply and cable input combinations, a list of available installations become available in the installation tab. And when I click on a particular installation, the table number that it associates with is shown here. Similarly, if I click on insulated conductors on a messenger, I expect to see 310.20, which is the table corresponding to this particular installation in NEC Article 310. So we can see another control here, equipment terminal temperature rating. This is a very important control. So as per NEC article 110.4, all our cable sizing calculations are limited to the terminal temperature. So let's say our insulation conductor, we have selected a conductor that is rated at 75 degrees centigrade maximum temperature or 90 degrees centigrade maximum temperature. Now that conductor being rated to a high temperature would allow a higher ampacity. But let's say on the same circuit, we're connecting it to a terminal or a connector or any other equipment that is rated less than 90 or 75 degrees centigrade, let's say 60 degrees centigrade. 60 degrees centigrade would limit our ampacity, available ampacity, allowable ampacity. So all our cable sizing calculations for that circuit would be based on the equipment terminal temperature, that is 60 degree, that is the lower ampacity as compared to the 90 degree or 75 degree centigrade. So these conductors have an associated resistance and reactance value. NEC only provides resistance and reactance values for one particular installations, that is insulated conductors in raceway. So that table in chapter 8, table 9, we get the resistance and reactance values, but those values they depend on the conduit type, and we define that conduit type over here. So this conduit type basically accesses different columns in that resistance and reactance table. So let's say I select PVC as the conduit type. I can see the references to these tables in these references you can find in the details. So we go into voltage drop, resistance value, we get this value, we extract this value from the table, NEC table, and the references we use table 9 and column number 5 for the resistance values. We can similarly see it for the reactance value, table 9, column 2 is used for the reactance value. So in the installation tab, you can also see two checkboxes for inside duct installations and inside tray installations. These checkboxes basically act like filters. When you click on inside duct, you can only see the ducted installations that are available. And when I click on inside tray, I can see only the installations with the cable. Now, all these cable tray installations have a different correction factor. So this particular installation has a correction factor of 0.65, which I can see in the corrections tab. Similarly, if I select the second installation, I expect to see a correction factor of 0.75, and these correction factors come from Article 392.80 in NEC. So when I click this, I should be seeing 0.75, which is as expected. So this is how cable tray installations basically give us a correction factor. So the installations that don't have supported NEC resistance and reactance values, the user can enter the resistance and reactance values that become available over here in the installation tab. They can enter the resistance and reactance values in ohm per 1,000 feet based on the data sheets or manual calculations that they have done. So when we click on inside duct, we see a list of ducted installations that become available. These installations are taken directly from the appendix B.2 in NEC. These are not part of the standard table coverage in NEC. These are additional special conditions. These results are based on special inputs that are defined on this in these appendix tables. So for the compliance purpose, we pass on an informative notice to the user that the installation uses the NXP calculations, and you have to validate your assumptions and obtain an engineering review for the. Now let's move to the corrections tab. Here we define the correction factors that are used to derate the cable, the conductor. So we have two modes over here. NEC mode basically uses the tables from the standard to apply the correction factors, and then there's also custom mode. In the custom mode, this control basically becomes editable and the user can enter any correction factor that they might already know. Otherwise, we use the NEC mode and we have two sort of corrections. One is the temperature correction that is based on ambient temperature, and the second correction is based on the number of conductors being bundled together. So all the NEC installations, they are based on some standard temperature. Let's say article in table 310.16 is based on 30 degrees centigrade tables. There are some other installations that are for 40 degrees centigrade, for example, table 310.17. And then we have ducted installations and underground installations that are based on an ambient temperature that is 20 degrees centigrade. But if your ambient temperature is different from the ambient temperature that those tables are based on, then there has to be a specific correction that has to be applied for the ampacities. Let's say our ambient temperature is 35. So the table 310.16 is designed for 30 degrees centigrade, but your ambient condition where you're trying to install the conductor is 35 degrees centigrade. In this condition, the tabulated values will have to be derated with a correction factor of 0.94. These derated values can also be seen in the detail section. We can see the correction factor coming up here. Then we can also see the circuit rating derated over here. So tabulated is the value from the table and derated value is after multiplying with the correction factor. Similarly, if multiple conductors are bundled together, we have a correction factor associated with that as well due to heating effects, mutual heating effects. If there's only three conductors, then NEC applies no correction factor. Correction factor is 1. But let's say if we have four conductors in close proximity, there's a correction factor that is associated with it as per NEC Article 310. That correction factor is basically added here. Similarly, if you go 50 conductors bundled together, the correction factor value would change and your conductors would have to be derated accordingly. In some cases, your neutral conductor also constitutes as a current carrying conductor, especially when it's a non-linear load with a high triplen harmonic profile. So let's go into harmonics tab, and on the fundamental 100 amps, let's add 50 amp of triplen current as well. So this would give us an informational notice over here that you have to consider neutral as a current carrying conductor if the major portion of the load is non-linear. This is directly from NEC. You might have noticed another control here, that is rooftop exposure. So as per NEC, if the conductor is installed on a rooftop at a specific distance, a minimum specific distance, there's and it is exposed to sun, there's an additional ambient temperature that is added to the standard ambient temperature, which is 33 degrees centigrade. If you check this on, that temperature, rooftop temperature added would be used in the cable sizing calculations as well. Obviously, there are some conditions where rooftop exposure is not possible. For example, the cable or the conductor is directly buried. In such cases, the rooftop exposure would not be available as a control. Also, for certain insulation types like SX, HHW, this control would not be available. Moreover, the cable sizing also uses a special installation, which is the single phase dwelling services. It basically refers back to Article 310.12. This basically doesn't use any corrections at all. So when this particular installation is selected, load current would be hidden because this particular installation sizes the cable based on the feeder rating. So we will only define the service feeder rating, no corrections would be applied, and voltage drop would be bypassed as well. Next, we look at the protection tab. In the protection tab, the user can select the overcurrent protected device, a circuit breaker, fuse, or keep it at as unknown. The only difference between circuit breaker and fuse is that as per NEC Article 240, we have different standard ampere ratings available for circuit breaker and fuse. Let's reduce the load current to 5 amps. Now the circuit breaker ratings start from 10 amps. So this is the minimum rating for the OCPD device that we're going to get with the load current of 5 amps. But we can see that there's a warning here. If we go into the warning tab, what this tells us is that this 10 amp circuit breaker is overrated for the load current of 5 amps. And it will also give us a suggestion that consider switching to a fuse for the lower rating options. So we can close this, and if we switch back to fuse, we will see that we might have a lower rating test. Yes, we have a 6 amps rating available. So even if we reduce it even lower, let's say 1 amps, we can see that we have a OCPD of 1 amp available in the NEC Article 240 as well. So we have another warning here. Let's look at that. So this warning is related to the equipment grounding conductor sizing. So EGC sizing basically depends on the overcurrent protective device. And the overcurrent protective device is 1 amps, and the EGC sizing basically starts with 15 amp protective device as per Article 250.122. Let's move on to the results. So in the cable size tab, I can see there's two tabs in the results tab, cable size and details. In the cable size, I can see the phase size, number of circuits. These are automatically calculated, spare capacity, neutral sizing, neutral number of circuits, equipment grounding conductor sizing that depends on article NEC article 250.122, number of circuits for EGC, voltage drop being calculated, and available fault current at the load end of the run. So here we can also, similar to all other calculators, we can manually size the conductors as well. So if I go into a manual mode, I can manually select the size to any particular size I want, and all other calculations would be auto calculated, the spare capacity, etc. And also we can increase the number of circuits. So in this three-phase scenario, if I change the number of circuits to two, if you remember in the corrections, we said multiple conductor adjustment. So if we're using two circuits of three-phase, now we have six conductors. So there's a warning here that you have to count each conductor in parallel set as a current carrying conductor for the multiple conductor adjustment. So based on this manual calculations, I'll go back here to the corrections tab and I'll use the correction factor of 6 for my ampacity calculations and then do my cable sizing. Similarly, if we go into the detail section, we can see the trail and all the references for all the calculations. If you click on total currents and power factors, these are basically used for unbalanced calculations as well. If you use three phase and unbalanced and you define unequal currents, you can basically see the neutral current, and if you add harmonics you can see the true RMS current as well. If I go into the harmonics tab, I randomly add some currents in here. I can see the true RMS values over here and the neutral current that is flowing here as well. I can see the power factor including harmonics, that would be your true power factor instead of displacement power factor. I can see my current carrying capacity of my phases, the operating temperature of my conductor. So now we have ampacity results for both insulation column and the terminal column, because our insulation is rated at 75 degrees centigrade and our terminal is rated at 60 degrees centigrade in this case. So let's expand the insulation and terminal. In insulation, I can see my derated ampacity is 460 amps and my tabulated ampacity is 460 amps because currently there's no correction applied. But let's say we add some correction as well. Let's add 0.5 something, 0.5. 0.5 correction is applied. Now derating ampacity that is shown here on the insulation would be exactly half of the tabulated current. And our dictating factor mostly depends on the lower of these ratings. So our tabulated rating is 760 amps, but our terminal rating is 640 amps. So the lower ampacity always dictates the cable sizing calculations in NEC. So we will use, but our corrections are always applied on our tabulated values of the insulation and not the terminal. So I can see all those ampacity values here. Similarly, I can trace for the neutral sizing. I can see the neutral temperature, the correction factor being applied. For voltage drop calculations, I can see the maximum length of run. I can see the resistance and reactance values. If they are from the NEC table, I can see the references for those tables as well. But if those values are from the user, then we will only see the resistance and reactance values as results over here. With harmonics added, we can also see the total harmonic distortion in each phase that we've added. Probably we didn't add anything in the phase 2. So yes, phase 2 was 0 amps, so it makes sense that it had 0 THD. Moreover, you can also generate a detailed report of your calculation from going here into cable sizing